Most drivers have no idea they're slowly destroying their engine with habits that feel completely harmless. I've spent 23 years rebuilding engines that failed decades too early, and the pattern is always the same. Owners convinced they were doing everything right. The truth is, your daily driving habits will either push an engine past 300,000 miles or kill it before it reaches 100,000. These 9 habits cause damage without warning, and most drivers are guilty of at least 3 of them. Habit number 9. Never letting your engine rev past 3,000 RPM. A customer brought in a 2019 Mazda last month with a rough idle and misfires across 3 cylinders. 42,000 miles on the odometer. Never tracked hard. Never revved above half throttle. The owner thought she was extending the engine's life by keeping everything gentle and smooth. When we pulled the intake manifold and scoped the valves, they looked like the inside of a chimney flue. Here's what's actually happening when you creep everywhere in 6th gear at 1,800 RPM, convinced you're being kind to the machinery. Your engine never reaches the operating conditions it was designed for. Combustion temperatures stay low. Blow-by gases linger in the crankcase instead of burning off through the PCV system. Carbon deposits accumulate on intake valves, piston rings, and combustion chamber surfaces because nothing ever gets hot enough or moves fast enough to clean itself out. This phenomenon hits direct injection engines hardest, and those are most of what's rolling off assembly lines today. In older port-injected cars, fuel sprayed directly onto the back of the intake valves and acted like a solvent, washing away deposits with every single combustion cycle. The valves stayed relatively clean as a byproduct of normal operation. But GDI engines inject fuel straight into the cylinder, bypassing the intake valves entirely. Those valves never see a single drop of gasoline. They just collect vaporized oil from the PCV system and blow by residue from the crankcase until they look like they've been dipped in roofing tar. The piston rings suffer too. Rings need heat, pressure, and cylinder wall contact to seat properly against the bore. When an engine never works hard, never sees sustained load, those rings never fully bed in the way engineers intended. Compression drops gradually over tens of thousands of miles. Oil consumption creeps up because the rings aren't sealing against the cylinder walls. By the time you notice blue smoke puffing from the tailpipe at startup, the damage has already accumulated beyond simple fixes. The controlled solution isn't complicated, and it doesn't require track days or aggressive driving that puts you or others at risk. Once a week, find a stretch of road where you can safely accelerate through the gears and let the engine breathe. Get it up to full operating temperature, then ask it to actually produce the power it was designed to make. Not redline abuse, not lugging it up hills in top gear, just normal spirited driving that lets everything heat up, expand to operating clearances, and burn clean. Italian tune-up, the old-timers called it. Turns out they understood something that modern drivers have forgotten. But carbon buildup isn't the only thing accumulating while you drive conservatively. There's something sitting in your fuel tank right now that's working against you. Habit number 8, habitually running the tank below a quarter. That low fuel light blinking on your dashboard isn't just a polite suggestion from the engineers. It's a warning that your fuel pump is working harder and running hotter than it was ever designed to. Your fuel pump lives inside the tank, completely submerged in gasoline during normal operation. That gasoline surrounding the pump motor isn't just fuel waiting to be burned, it's coolant. The liquid absorbs heat from the electric motor and carries it away, preventing the pump from overheating during the thousands of hours it operates over a vehicle's lifetime. When you habitually run the tank low, that pump sits exposed to air, pulling fuel from the very bottom of the tank where decades worth of sediment, rust particles, and condensed moisture have accumulated into a layer of contamination. I replaced a fuel pump last week on an Accord with only 67,000 miles. The owner routinely ran it down to the last gallon before pulling into a station, sometimes driving past the low fuel warning for 20 or 30 miles. When we dropped the tank, the pump's inlet screen was packed with debris that looked like wet coffee grounds. The motor itself was burned out from heat stress because it had been running exposed to air instead of submerged in cooling fuel. A part that should have lasted 200,000 miles failed at $67,000. The repair invoice told the whole story. The pump itself runs around $150 for a quality replacement, but accessing it meant dropping the entire fuel tank, which adds labor. Then we had to flush the fuel lines and clean contamination from the system before installing the new pump. A $150 part turned into a $680 job, not counting the tow truck that brought the car in after it died at a traffic light. The math never works in your favor when you gamble with fuel level. You might save 5 minutes by skipping the gas station on your way home, but you're betting against a component that can strand you on a highway shoulder with no warning. Most vehicles are engineered with the assumption that drivers will maintain at least a quarter tank under normal circumstances. Some have saddle tanks or irregular tank shapes that make the quarter tank threshold even more critical for pump longevity. Check your owner's manual for specific guidance on your vehicle, but the baseline rule works for almost everything on the road. Treat a quarter tank like empty. Fill up before you reach that mark. The pump lasts longer, the fuel stays cleaner, and you never find yourself calling for a flatbed because you pushed your luck one time too many. That's money sitting in your tank waiting to save you grief. But the damage you can do in the first 60 seconds after startup costs even more to repair. Habit number 7, flooring it in the first 60 seconds after start. Cold starts are when engines face their greatest vulnerability, and most drivers treat them like the car's already warmed up and ready to perform. When you turn the key or press the start button, oil is sitting in the pan at the bottom of the engine. Pressure hasn't built yet. The lifter galleries running through the cylinder head are dry. The rod bearings, cam lobes, and timing chain tensioners are all running on whatever thin film of oil managed to cling to metal surfaces overnight or during the hours since you last drove. Full throttle in this state isn't spirited driving. It's metal-on-metal contact happening at the worst possible moment, before the lubrication system has done its job. The oil pump needs time to build pressure and push oil through narrow passages to every bearing surface in the engine. Demanding maximum power before that happens loads components that aren't ready to handle it. Turbocharged engines take it even harder than naturally aspirated ones. The turbocharger bearings depend on pressurized oil flow that simply doesn't exist during the first few seconds of operation. The center cartridge spins at tens of thousands of RPM, supported only by a hydrodynamic oil film. Without adequate oil pressure, that bearing wears at an accelerated rate. Variable valve timing systems face similar challenges. They need oil pressure to actuate the cam phasers properly, demand full power before that pressure arrives, and you're commanding the engine to do things it physically cannot accomplish without damage. I've seen the long-term results of this habit during teardowns on high-mileage engines. Rod bearings scored and spun from repeated cold start abuse. Timing chain guides worn completely through because the tensioner couldn't maintain proper pressure during those critical first moments. Camshaft lobes with visible wear patterns that shouldn't exist at 90,000 miles on an engine that otherwise received regular maintenance. The damage from cold start abuse doesn't announce itself immediately. It accumulates silently over years of mornings, where drivers backed out of the garage and immediately floored it to merge onto a highway. The wear happens in microscopic increments until something finally fails at a mileage that seems premature. The window requiring patience is remarkably short. 30 to 60 seconds of idle allows the oil pump to build pressure and distribute lubrication to critical surfaces. Then gentle driving until the temperature gauge begins moving off the cold peg. You don't need to baby the engine for 10 minutes, like your grandfather did with his carbureted pickup. You just need to give the oil system time to do its job before asking for power. After that first minute, drive normally, but those first 60 seconds matter more than most drivers will ever understand. If any of this has opened your eyes to habits you didn't realize were causing harm, hit subscribe. It costs you nothing and helps more drivers avoid the same expensive mistakes. Now, there's another throttle habit that causes even more internal damage than cold start abuse, and almost nobody talks about it because it feels like the right thing to do. Habit number 6. Lugging the engine to save gas. That 1,200 RPM you're holding in 5th gear, climbing a highway on-ramp isn't fuel efficiency. It's mechanical stress that your engine wasn't designed to handle. Lugging happens when you ask the engine to produce meaningful power at RPMs too low to support the load you're placing on it. The engine bogs down. The car shudders and vibrates. Most drivers respond by pressing the accelerator harder instead of downshifting to a lower gear, which only compounds the problem by demanding more torque at RPMs where the engine can't deliver it efficiently. Inside the cylinders, during lugging conditions, pressure spikes occur because the air-fuel charge has too much time to compress before the spark plug fires. This extended compression time allows heat to build in ways the combustion chamber wasn't designed to handle. Pre-ignition and detonation follow, creating pressure waves and shock forces that hammer the piston crowns and put bending loads on connecting rods. Those rods are incredibly strong in tension and compression along their axis, but they weren't engineered to handle the sideways bending forces that detonation creates. Small turbocharged engines stuffed into heavier vehicles suffer from lugging more than almost anything else on the road. Manufacturers love pairing a 1.5-liter turbo four-cylinder with a 3,500-pound crossover because the power numbers look impressive on the window sticker, and the EPA fuel economy ratings benefit from the small displacement. But those engines rely entirely on boost pressure to compensate for their lack of displacement, and building boost requires RPM. Lug them constantly in high gears under load, and you're asking a small engine to behave like a diesel under conditions it absolutely cannot tolerate. The symptoms of chronic lugging don't appear right away. That's what makes this habit so insidious. Bearing fatigue accumulates over tens of thousands of miles of abuse. Piston ring lands develop microscopic cracks from repeated thermal shock that slowly propagate until the ring breaks. By the time something actually lets go catastrophically, the repair bill often exceeds what the car is worth. The fix requires nothing more than paying attention to what the engine is telling you. Downshift when you feel resistance. If the engine sounds like it's struggling or the car shudders under acceleration, it is struggling, and you need to give it mechanical advantage by selecting a lower gear. Let the engine rev into the range where power comes easily and naturally. Fuel economy actually improves when the engine operates in its designed efficiency band rather than straining at the very bottom of the tachometer under heavy load. The gas you think you're saving by lugging gets burned anyway through inefficient combustion, and you're adding the future repair costs you'll face when something fails prematurely. And while we're correcting fuel-saving myths that actually cost drivers money, there's one morning habit that needs to disappear entirely. Habit number 5. Idling for 5 minutes to warm it up. Your father did this because his carbureted engine genuinely needed it to run properly on cold mornings. Your fuel-injected car absolutely does not. Extended idling keeps the engine operating in open-loop fueling mode, running deliberately rich until the oxygen sensors in the exhaust reach operating temperature and closed-loop fuel control takes over. That extra fuel dumping into the cylinders during extended warm-up doesn't just waste gasoline. It washes the protective oil film off cylinder walls, dilutes the oil sitting in the crankcase, and accelerates wear on rings and bearings that depend on that oil film for protection. Meanwhile, every other component in the drivetrain sits completely cold. The transmission fluid isn't circulating because the car isn't moving. The wheel bearings aren't warming up. The differential gear oil stays thick and sluggish. Everything except the engine block remains at ambient temperature because there's no mechanical load generating heat through the drivetrain. You're warming one component while neglecting everything else that needs to reach operating temperature for optimal performance and longevity. 30 to 60 seconds of idle is all any modern fuel-injected engine needs before you begin driving gently. Under light load, the entire drivetrain warms faster and more evenly than it ever could sitting stationary in your driveway with the engine idling. The thermostat opens sooner because combustion generates more heat under load. The transmission fluid begins circulating and warming. The catalytic converter reaches the temperature where it actually functions and begins cleaning exhaust emissions. Extreme cold does change the calculation slightly. Below -20 degrees Fahrenheit, an extra minute or two of idle helps thick oil flow more freely through narrow passages before you ask anything demanding of the engine. But the 5 to 10 minute warm-up rituals most drivers perform in 40-degree weather aren't helping anything. They're just burning fuel, diluting oil, and adding unnecessary wear while accomplishing nothing the drivetrain actually needs. Start it. Wait 1 minute maximum. Drive gently until everything reaches operating temperature. That's the entire modern warm-up protocol. But what happens immediately after hard driving matters just as much as what happens before you begin asking for power. Habit number 4, shutting off immediately after hard driving. Turbochargers spin at speeds exceeding 100,000 RPM during boost conditions. When you shut the engine off, that spinning mass doesn't stop instantly. It coasts down over several seconds while residual heat continues soaking through the system. The turbo's center bearing relies on pressurized engine oil for both lubrication and cooling during operation. Oil flows continuously through the bearing housing, carrying away the enormous heat generated by exhaust gases that can exceed 1,000 degrees Fahrenheit on the turbine side. When you kill the engine immediately after spirited driving, that oil flow stops completely while residual heat continues migrating from the turbine wheel through the center section toward the bearing. The result is called oil coking. The trapped oil carbonizes inside the bearing housing because there's no fresh oil flow to carry heat away and no circulation to prevent the oil from reaching temperatures where it breaks down chemically. These carbon deposits accumulate in the bearing housing over time, restricting future oil flow and accelerating wear on subsequent drives. The turbo slowly destroys itself through repeated thermal cycles that end abruptly instead of cooling gradually. Some modern turbocharged vehicles include electric auxiliary coolant pumps that continue circulating fluid through the turbo after you shut off the engine and remove the key. Others have software-controlled turbo timers built into the engine management system, but not every turbocharged car includes these features, and many that do still benefit from 30 to 60 seconds of idle after aggressive driving to let temperatures stabilize throughout the system before shutdown. If your car runs a naturally aspirated engine without forced induction, this particular habit doesn't apply to you. Shut it off whenever you want. But if you're driving anything with a turbocharger manufactured in the last 15 years, treat the cool down idle as part of every spirited drive. A minute of patience costs you nothing but a few seconds of your time. A cooked turbo costs between $1,500 and $4,000, depending on the vehicle, plus labor, plus the diagnostic time required to confirm the failure. The cumulative damage from these habits compounds faster than most drivers expect, but nothing compounds quite as quietly as the next one. Habit number 3, only ever making short trips. 5-mile commutes repeated day after day are quietly destroying engines across the country, and the drivers have no idea anything is wrong until major symptoms appear. When an engine never reaches full operating temperature during a drive, several destructive processes accelerate simultaneously. Fuel dilution increases dramatically as unburned gasoline washes past the piston rings and contaminates the oil sitting in the crankcase. The oil level may actually rise on the dipstick as raw fuel accumulates. Moisture from combustion byproducts condenses on cold internal surfaces instead of evaporating, then mixes with blow-by gases to form acidic compounds that attack bearing surfaces and promote sludge formation throughout the oiling system. The oil never gets hot enough to boil off these contaminants through normal evaporation. The PCV system never flows enough volume to purge accumulated moisture and fuel vapors from the crankcase. Over months and years of exclusively short-trip driving, the oil transforms into a corrosive slurry that accelerates timing chain stretch, cam bearing wear, and piston ring degradation. Components that should last 200,000 miles start failing at 80,000. GDI engines suffer worst from short trip abuse because they're already prone to intake valve carbon buildup under normal conditions. Add chronic low-temperature operation that prevents any self-cleaning during combustion, and those deposits accumulate even faster than they would otherwise. Hybrids face similar challenges when the gasoline engine cycles on and off repeatedly for electric assist without ever running long enough to heat soak properly and burn clean. The controlled fix for short trip damage is remarkably straightforward and costs nothing but time. Once a week, take the car on a 20 to 30 minute highway drive at consistent speed. Get everything up to full operating temperature and hold it there long enough for the oil to reach thermal equilibrium throughout the crankcase. Let the engine actually work under load for an extended period. This single habit offsets most of the damage that short trip driving causes during the rest of the week. Think of it as preventive maintenance you perform without tools, without parts, and without scheduling a shop visit. Habit number 2, revving hard in park or neutral. That quick blip of the throttle you do at the car meet to make the exhaust bark isn't as harmless as the crowd reaction suggests. Without drivetrain load absorbing rotational energy, the engine accelerates far faster than the rotating assembly was ever designed to handle during normal operation. The crankshaft, connecting rods, and pistons experience acceleration forces that simply don't occur when the engine works against resistance from wheels on pavement. Valve springs get tested at compression and extension rates they weren't engineered to see repeatedly. Oil control throughout the engine suffers because the sudden RPM spike outpaces the oil pump's ability to maintain steady pressure at every bearing surface simultaneously. At high RPM with no external load, oil can actually drain away from where it's needed most in the engine. The windage tray beneath the crankshaft and the oil pickup tube are designed for operating conditions where the engine works against meaningful resistance. Unloaded revving changes the fluid dynamics inside the crankcase in ways that create momentary oil starvation at the exact bearing surfaces most vulnerable to damage at high RPM. Flat plane crank engines designed for high-performance applications and vehicles equipped with dry sump oiling systems tolerate unloaded revving somewhat better than typical consumer vehicles. But the average sedan, crossover, or pickup truck running a conventional wet sump oiling system wasn't designed for repeated high RPM blips in park or neutral. The engineers assumed you'd rev the engine under load while actually driving. The irony most drivers don't understand is that unloaded revving is actually harder on internal components than the same RPM achieved under load during actual driving. With drivetrain load, acceleration happens gradually as the engine works against resistance. Without load, everything spikes instantaneously to whatever RPM your right foot commands. The stress isn't distributed over time. It concentrates in a single moment of maximum acceleration force. If you genuinely want to hear your exhaust note, do it while driving at legal speeds on appropriate roads. The engine will thank you for the consideration. One habit remains to discuss, and it affects a larger percentage of drivers than any other on this list. Habit number 1, using regular when premium is required. Modern NOx sensors allow your engine to survive lower octane fuel than the engineers specified. They do not allow it to thrive on that fuel or perform as designed. When the engine control unit detects detonation through the NOx sensors, it responds by retarding ignition timing to prevent immediate damage from uncontrolled combustion. The engine continues running. It doesn't blow up on the spot, but every single mile driven on insufficient octane fuel means chronic micro-detonation events occurring inside the combustion chambers, reduced power output because timing can't advance to optimal positions, degraded fuel economy because combustion efficiency suffers, and cumulative mechanical stress on pistons, rings, and rod bearings that weren't designed for constant detonation loading. Drivers justify using regular fuel in premium required engines by pointing to the cost savings at the pump. 15 or 20 cents per gallon adds up over time, they reason. But that math falls apart completely when you factor in the efficiency loss from retarded timing. Less timing advance means less power extracted per unit of fuel burned. You end up consuming more gallons of regular fuel than you would have consumed of premium to cover the same distance at the same speeds. The theoretical theoretical savings at the pump evaporate into the exhaust, and the internal wear accumulates invisibly until something finally fails. This guidance only applies when the fuel door label or owner's manual explicitly states that premium fuel is required for your specific engine. The word recommended carries different meaning entirely. Required indicates that the engine's compression ratio, turbocharger boost pressure levels, or variable valve timing profiles absolutely demand higher octane fuel to operate as designed without knock-limiting intervention from the ECU. Recommended means the engine can adapt to regular fuel with minimal penalty under most driving conditions. Check your documentation carefully. If it says required, use premium fuel every single time you fill the tank. The cost difference over a full year of driving amounts to a few $100s at most. The cumulative engine damage from tens of thousands of miles of knock-limited operation costs far more than you'll ever save at the pump. 9 habits. Most cost nothing to fix. All of them cost thousands to ignore. Your engine wasn't designed to fail at 100,000 miles. It was designed to survive driver behavior that makes failure inevitable. Change the behavior and the mileage takes care of itself.